from PHP to Python. So let's start with a show of hands. Can you put your hand up if you've ever been dealing with some massive, old, crufty piece of code and you wanted to just completely tear it up and rewrite it from scratch?
Okay, wait. You want to tear up the video crew because we're going to ask them, can you start that again? Because we didn't actually save it.
All right.
This far into it and we've killed. Sorry.
Yeah, we're going to restart so I can get my timer correct. All right. Good? Go. All right. Morning, everybody. I'm Sam. This is from flying Circus to Holy Grail, migrating the Twilio API from PHP to Python. So let's start with a show of hands. Can you put your hand up, please, if you've ever wanted to just tear up some completely crufty, old, janky code base and just rewrite it from scratch? All right. For the video, we've got a room full of hands. Keep your hand up if you've actually pulled this off. And we have 1, 2, 3, couple shaky hands. All right. So clearly something's wrong here. We've all seen this go wrong, right? Our old code sucks. Let's rip it out and redo it. And then 12 months later, we come back and we've gotten nowhere. Or we thought we had a replacement and we deployed it and it imploded. So since I'm standing here and I'm talking about replacing systems, there's obviously another way. So, hi, I'm Sam. That's my Twitter handle. I have opinions sometimes. I've been at Twilio for about 3 years. 2 of those were on the API team, where we did, in fact, migrate from our 7-year-old flying circus of 500,000 lines of PHP code to the holy grail of federated microservices and Python. Today, I'm going to talk about techniques for replacing those legacy systems using this project as a case study. So if you're not familiar with Twilio, we provide communications as a platform. So as a developer, you can sign up for a Twilio account and use us to build communications. So phone calls, text messages, MMS, WebRTC, chat, all sorts of things, into your apps, wherever you need to. To put a little more context on the work I've done, the REST API is critical to our platform. At peak, we process 5,000 requests per second, and over the last year, we've had over 4 nines of uptime. So with that in mind, I want to set the context for this case study with a really brief history of the Twilio architecture internally. So in ancient history, by the company time, in 2008, we had one product. It was Twilio Voice. You could make phone calls, and you could direct them, connect them to other phones, make conferences and things in real time. It's still pretty cool. You should check it out. We also had exactly 2 code bases. We had the PHP code base, and we had the Java code base. Java was responsible for everything involving the phone network. So it actually talked to phone carriers and moved media back and forth. And that was it. The PHP codebase handled everything else. They interacted by way of a MySQL database, which is that nice database in the middle of this picture. And pretty much worked like this. You would make a post request to our calls endpoint to start a new phone call. The PHP code would say, great, are you who you say you are? So it would authenticate your request, it would validate the parameters you sent in, rate limit, etc., and say, great, everything looks good. It would drop a row into the calls table in status init. The Java code base would be pulling this table in real time and find all the init calls and pick up a phone line to the carrier and dial, and then you'd be off to the races. As your call progressed, Java would write back status information to the database, and you could query that through the API, where PHP would just go and pick up a database handle and go look at your calls and tell you how they're doing. So this is pretty much how we ran for a long time. The PHP code also ran the website, the billing backend, our internal admin tools, and over the years it grew. We added some more features, like SMS. Fortunately, by the time we launched SMS, we knew how to queue better, so we had a different system in place for queuing the outbound messages. But we still relied on PHP talking directly to the database for just about everything else. And now we're 5 years later. So now we're in 2013. And we realized that this architecture had a few problems. So first up, too many slides. First up, this system was hard to deploy. It was one repo with, like I said, literally 500,000 lines of PHP in it that was deployed across multiple systems performing different functions. So the API, the website, the billing system. But the core logic for all of that was shared. So changing something on the website might very well break functionality in the API or the billing system, or vice versa. So deployments for this thing usually looked like 10 or 15 developers basically locked in a room with one massive feature branch ready to go out and burning things down by hand, verifying that everything worked right. Everything that we knew we were changing. Sometimes there were surprises. This took hours. This code was difficult to understand in two senses. First, it had grown so fast that it wasn't very well organized, so figuring out what logic lived where and why usually took a senior dev and an afternoon. And second, and this is kind of the harder thing, is it wasn't well instrumented, so operationally it was difficult to understand. We never took the time to go through and apply fine-grained metrics to our systems, so finding performance problems and debugging them was really difficult. And finally, it was operationally brittle. In the API layer, this surfaced as one major flaw. We were running a single fleet to handle all of the API traffic, and that traffic varied widely. So on the one side, we have outbound messages and outbound calls, which usually process in about 100 milliseconds because all you're doing is just queuing something up. But you also have somebody coming in and asking for a list of 1,000 calls, sorted and filtered, and that could take longer, especially if the databases were behind. Add in synchronous I/O thanks to PHP's lack of any alternative execution models, and we ran into trouble pretty quickly. So sorry, David Beasley, we don't run threads in prod anymore. Any slowdown in one resource, therefore, even if everything else was healthy, would quickly exhaust our synchronous worker pools on the web server, the API servers, excuse me, and lead us to a state where the API couldn't serve any traffic to any resource, anything, even the things that were unrelated. So as an API provider, this is the worst possible failure mode we had. We felt terrible about this. We weren't able to take traffic because we were stuck handling things that were never going to succeed. So what can we do? We have 500,000 lines of PHP handling this critical API for our systems that's not scaling either with our developer team's growth or with our customers' traffic. We knew if we set out to rewrite it from scratch in one go, we'd probably almost certainly fail. So what did we do instead? We decided to tear it apart and replace it in pieces. And that's what I'm going to talk through for the rest of today. Thankfully, the API team wasn't in a vacuum over those 5 years. Engineering had figured out in the meantime that instead of having one giant monolithic service to deploy that does everything, it's usually a better idea as you scale to build small single-purpose services. And we built a couple of them to handle new features as we were building them out, and even hooked up the PHP API to a couple of them in some cases. So this is the service-oriented architecture. It's definitely inspired by Amazon. If anybody's familiar, about 10 years ago, I'd say, right around the advent of when AWS happened, Jeff Bezos had put out this mandate that nobody's allowed to link any other team's services, so you can't link their libraries, you can't use their databases. The only way you can talk to other services inside of the system, inside of the Amazon, is over the network through an API call. It really forced them to reevaluate how they were doing things, and that led to the growth of Amazon Web Services. And we decided that we liked this model, and we picked it up. So we picked REST as our internal API standard, which got us thinking. So we have all these internal systems, so calls, SMS, numbers, and so on. They all speak REST, and our public API speaks REST. So couldn't we just map one of these things to the other and call it a day? Which is what we did. We wrote a simple, powerful app for transforming and routing REST requests. We identified the internal systems that had grown to feature parity with existing API endpoints and move resources over from one to the other. We call that app Starship because it federates the API. You're welcome. I didn't name it. And it's a Python app. It's built in Flask with Flask RESTful, which is an open source framework that we'd put together for quickly building REST APIs in Flask. And it uses requests for doing HTTP requests. As of the end of 2014, it handles 100% of the Twilio API traffic. This architecture, so with Starship in front of all of our internal services, this architecture solves everything that we disliked about the PHP API, and then some problems that we didn't even know we had. So here's what that looks like today. We have this vast array of services implementing all the Twilio functionality, and they all have private APIs internally. And Starship acts as the public front door to the API and unifies them into the cohesive public interface that actually a previous speaker was just saying he enjoyed so much. Critically to our success with this architecture is that Starship provides all the common elements of the public API. So that's authentication, validation, rate limiting, and so on. It lets all the product teams that are building those individual services not worry about any of those problems. If we hadn't done that, right, we could have just a simple HTTP load balancer, right, or router that only knows where to put individual requests but doesn't know how to do any of the semantics associated with them. But then every individual team, so the messaging team, the voice team, the phone numbers team, would have to worry about how to do authentication, how to do rate limiting, how to do validation, and do all of those things at scale. So instead, the API team handles those once for everybody, and it lets everybody else move a lot faster. We call this the Proxied Resource pattern. So given that external API endpoint and an internal service that exposes something that does the same semantic work but might be formatted or structured a little differently, we define a mapping from one to the other. And that, for example, don't worry if you can't read this, it's small, but just they're shaped differently, right? These both represent a phone number in the Twilio platform. On the left, we have the internal representation, which has all this extra information pertinent to actually running Twilio. And on the right, we have what our customer cares about. So to get from one to the other, we have the core of Starship, which is this configurable engine that can apply all these transformations. So authentication, rate limiting, validation, mapping from the external request to the internal request, routing the request to the right place, and then doing the same thing on the way back out with a response. And all you do is write a config file that defines both sides of the API, and the framework takes care of the rest. So it's very fast for us to add or modify resource definitions. All right, that's the end of my summary of where we were and where we are today. And I'll talk through what we gained from doing this. There was obviously a lot of risk in moving all of that API traffic off of a system that we knew worked, even if it had some operational issues. But we also gained a lot. Gained some things like fixing our deployment problem. So now it's a matter of minutes to add a new API endpoint or reconfigure an existing one, because all you have to do is change Starship's configuration and redeploy it. And the teams responsible for the internal systems implementing all of our products can deploy those whenever they want without worrying about breaking something on the other side of the world. And automated testing on both sides of these interfaces between Starship and the internal services and across that service boundary help us ensure we don't break things. We also gained a lot of flexibility. Having a full-on Python app in the routing path for our API means we can route based on pretty much anything. We can do percentage-based rollouts of new features. We can use account flags because the API is aware of those. We can even shadow internal services by standing up a new release of something or a replacement for something and copying the traffic over so we can test with real traffic without affecting the customer response. And we fixed all those operational issues. So Starship is much, much, much more fault tolerant. We moved to async IO with G-event, not the actual async IO library. We're not on 3 yet. But because we're using asynchronous IO now, we can handle orders of magnitudes more in-flight requests. We no longer fall over just because one thing slowed down. We also took the time to go back and add instrumentation. And this is actually really easy because Starship was the one place we had to add it. And we now get this single vantage point to inspect the performance of all of our services. Here's 2 examples of that. This is latency to our API resources grouped by the internal service that handles the request. So you can watch this. This is pretty much a normal day. There might be a couple spikes. I didn't actually dig through this, but yes. So you can watch this. We can watch this and anticipate growth over time, right? We can say, oh, this service is slowing down because request volume is going up, and we can fix our problems before they become outages. And then very similarly, we can watch a single endpoint's performance with the timing split out by every phase of the operation, right? So there's a line here for how long it took to authenticate the request, for how long it took Starship to validate, and for how long it took the internal service to respond and everything. This graph is just showing a little bit of seasonal traffic. We peak on the hours pretty regularly, causing our reads to be a touch slower, but within normal limits. But again, we can find out, for example, with this, if we change something in the authentication service, whether we've slowed down. Both of these things we really had no idea before. We'd say, oh, the API got slower. Well, what did we change? We had no idea. Now we do. So that's what we did. But how? How do we move 5,000 requests per second safely without causing downtime for our customers to these new services? So Starship wasn't a new idea at Twilio. It came about in 2012 or so. Like I said, as we started rolling out new functionality in the service pattern, we put Starship out for new stuff, and it took us a while to decide eventually that we wanted to go all in on it and deprecate the old PHP API. So for the rest of the talk, I'm going to talk through how we did that. So how we planned out that architectural change, the intermediate steps we took along the way, and mostly the testing and deployment strategies we used to get this out. So first up on planning. Plans are good. You should have one. I have more detail than that. I think the most important thing I want to say on planning is that you should identify the granularity at which you want to break apart your existing code. So this could be if you have a bunch of web services, you should figure out whether you want to break it into logical groupings of objects or operations or even just functions, right? Figure out where you want to tear it apart on what boundaries, because that's going to determine how much work you have to do and the right abstractions to implement as you go forward. And once you've got that, make a list of all the things you need to replace and put it in order. So ordering your list of stuff to do, it's tricky, but I say you should start small. So find a couple things that aren't very mission critical or handling all the traffic for your services, and start with those. Make sure you can validate the pattern you've chosen and that everything works. But there's also a competing drive here, which is that you want to realize some benefits from this project, right? What we always hated about doing big bang rewrites is that you have to stop all your work for a year, right? But if you're moving things in pieces, you can find the really critical items, replace those, and unblock feature work, right? So don't procrastinate. Once you've proven that your architecture is going to work, go after the big stuff, because that's where you're going to unblock all those other people waiting to do new, exciting feature work, and you're going to reap the most benefit. All right, so architecturally, you also need to think through what you're doing. So don't just pick up a machete and start hacking away that old system and replacing pieces. Pick off reasonably sized chunks and deploy them one at a time, like I've been saying. This sounds hard, right? Fortunately, the fundamental theorem of software engineering applies. We can always solve a problem by adding indirection, except maybe the problem of too many layers of indirection. So add some indirection. Think of this as a shim in front of your old code that lets you isolate it from whatever's calling it and put it alongside your new implementation that you're going to be building, and lets you decide and dispatch between the two based on what you're moving, what you've moved, and what you're ready to move. So the most critical piece here, as I said earlier, is to find the right level to add this at. If you go too low, you're going to spend all your time configuring how you do your dispatch. And if you go too high, you're not going to be able to work in chunks that are small enough to deploy safely or quickly. For us, to give an example, we did this with our HTTP server. We fronted both systems with Nginx, and I'm not going to put the config file up because it's about 10,000 lines and it's really janky. But we just used Nginx to route requests to one stack or the other based on the method and the path of the request. So for the longest time, posting to the calls endpoint, because that was our oldest and most delicate thing, still went to the PHP stack, while pretty much everything else had moved to Starship, and we finally managed to cut everything over. But that's how that works. And keep it simple. Just make sure that whatever you're using to do that dispatch in front of your old system and your new system is simple, easy to debug, because depending on what you're replacing and how big it is, you're probably going to be running with it for a long time. We ran with Nginx in that configuration for a couple of years. So that's where I am on architecture. Let's go on to testing. Once you've got this ready to go, you should start thinking about how to test it. Specifically, how to test your replacement implementations as you roll them out and make sure that they behave the same way as your old systems. If your legacy systems are like our PHP stack, this is both a blessing and a curse. You have a great opportunity to improve your test coverage here, but you're starting from, let's call it, not much. And unfortunately, there's a couple of tacks to take here. Before I go into those, I want to talk about the test pyramid. This is actually one of the more useful things to come out of the XP and Agile schools of development. And really, it just states that you should have multiple sets of tests and organize them based on how much of the code they're testing at once. It's really about boundaries. So you can see you've got unit tests, integration tests, and so on. And it's about how many boundaries you're crossing in your test case. And the idea is that the more boundaries you cross, it's slower to write the tests and slower to run them because you're invoking more code and you have to set up more of the world before you test whatever you're testing. So you should have more stuff at the bottom in your unit tests, right? Test really small pieces, test them very thoroughly, test a lot of them, and make sure they're fast to run. And as you go up, you should have fewer things because it's going to take you more time to write them and more time to run them. It lets you focus your effort in testing appropriately and test everything at the right level. To walk through what that looks like for Starship, it works something like this. The unit tests for Starship cover the internal logic that is specific to what Starship does, right? So this case of mapping one API request to another and performing a bunch of work on it before we do that. So we test things like the auth functions, the serializers, right? Can we round trip through our JSON formatter correctly, and so on. So mostly the unit tests are calling individual functions in isolation, or sometimes with mocks if we can't really tear the side effects out of the function. This test suite right now has about 1,200 tests, and it runs in 3 seconds. So that makes it something that we can run after every commit when we're working in a feature branch on Starship, right? You just continue, make a commit, change something, the test pass. Make a commit, change something, do the test pass. We also have integration tests. These are external to the Starship proxy logic, but we fake out the client and we fake out the downstream service that we're depending on. So the question they're answering is, take all the Starship code and then fake out the things on either side of it, right? Which are the network client that's talking to it and the service it's talking to. And if we assume that both of those are correct, does Starship do the right thing? We have several hundred tests here. They cover all the API endpoints and methods with at least one test case. And they take about 30 seconds to run. So it's still kind of something you can do locally as you're developing. And third thing we have is cluster tests. You might refer to these as functional tests, end-to-end tests, acceptance tests. They have a lot of names. These run against a complete Twilio cluster. So in our staging environment, with everything turned on, if we treat the entire system as a black box, assert that everything works together correctly, if we send in a request, it should do all the work we expect it to do and give us the response we expect. Critically, we have to run these when either side changes, right? So if we change something in Starship or if we change something in, say, the SMS service, we need to run these to make sure they still work together. We have a couple dozen tests in this suite, and they take about 5 minutes to run because they're doing a lot more work, right? We're actually using a live network, we're using live databases, we're actually making stuff happen. And then finally, we have manual tests. So if we're adding new endpoints or making a lot of changes that are very sweeping, we'll sit down with the PMs or the engineers responsible and walk through it by hand. And these are often the basis for new cluster integration tests. We'll take these test cases we designed and save them so we can automate them for the future. Next thing in testing is you should make it easy to write test cases. A lot of the time, when you're testing a big system, you'll end up writing a bunch of test cases that look really similar, right? So we've got some function or we've got some service, and we need to call it with 100 different arguments and assert that the response is correct for everything. Automate this as much as you can. Find those common cases and write library code or helper functions to make that go fast. Because eventually the day is going to come when you change something either in the logic that you're testing or in how you're going to test it. And if you copied and pasted those 20 lines of setup code 100 times, ouch. If you did it once with a library function, or actually with these neat tricks I'm going to show you next, you only have to change it once, and it's going to hurt less. So thankfully, we're in Python, and we have some really great testing libraries available to us. This is an example of how to do this with nose. So it's obviously a toy example, but you see down underneath, we have a check function that says this is actually doing the work of the test case. So it has some assertions in it, and it takes some arguments about what data to perform that assertion over. And then above, we have the actual definition of the test runner, whereas we just use this generator. And so the nose runner says, oh, I found a generator here. Everything that comes out of that generator is a separate test case, and it treats them as such. And you'll get nice, broken up output based on which pieces of data in that input sequence failed and which ones passed. Looks very similar for PyTest. They use a decorator instead of a generator, but you can see the same thing is going on here, right? We define a test function that takes the arguments and the expected output, and then we run it through with a bunch of test cases. These are toys. Like I said, in the real world, our test definitions have 10, 20, 50 lines of code in them, and so the benefit of doing this is much more apparent, right? If you had to change 50 lines of code 100 times because you had 100 different arguments, it's going to suck. And finally, I'm going to talk about throwaway testing. Sometimes your tests shouldn't live forever, especially for a project like this where you're replacing one system with a work-alike. And most critical piece is, does it actually work like the old thing? You're going to end up writing a bunch of tests that are brittle, and we're going to talk through response diffing, which is the example of how we did this with Starship, right? So we had the PHP implementation of the API, and we had Starship, and they needed to expose the same interface. So we wrote down a bunch of requests to run, and we said, OK, great, here's what to run through. And we wrote a script. You could do this with Bash, right? You can do curl and pipe it out to a file. Run requests against the known good implementation, right? And save all the results. And then take your new system, run that same list of requests against it, and then diff. Like literally just run the diff command. This is really easy to write. It's really easy to run. It tells you if you're correct. It'll tell you if you're wrong, but it really won't do a good job of telling you why. It's brittle, right? So if you break something, and it's hard to figure out why because you're basically staring at line by line, byte by byte diff. And that also leads to why you should throw these away. So you should use these. You should write up something like this if it makes sense to do so. Run it to assert that your re-implementation works the right way, and then get rid of them, because the moment you come back and want to change something, even if it's semantically the same in your new system, if it changes the formatting, right, like, oh, great, you added a new line in a JSON file, every one of these tests breaks. It sucks. So don't keep them. They're a really quick, cheap, one-off validation that you've replaced something with a correct re-implementation, but they're not good as a long-lived test suite. OK, so to recap on testing, just write multiple sets of tests. Remember the pyramid. Test everything at the right level. Identify and accelerate those common cases. And machine generate tests or do some similar tricks like that when they're useful, but don't rely on those long term because they're hard to debug, they're brittle, and they're not worth keeping. So that brings me to the last subject, which is deployments. I think we can all agree that deploying code should be easy, right? We want it to be small to minimize the risk of the changes we're making. We want our deployments to be fast to minimize the overhead, right? They're a tax that's placed on our development time. And we want them to be simple operationally because we want to minimize the complexity. Every time a human has to do something to deploy code, it's a chance to screw up. So I'm not going to dig in on this as far as optimizing your build and deploy pipeline. There's a lot of writing on this. People smarter than I have written blog posts or books even. But it comes down to automate whatever you can, right? Just make it as fast and as easy as possible for anybody who's deploying changes to get it done. What I am going to talk about deployment-wise is a couple extra tricks you can do. And people have talked about this before, but this is really helpful, especially when you're replacing a system for getting rid of the legacy implementation. Shadow deployments. So you might have heard of this as dark launches. So the trick here is you just copy your requests, right? So at the HTTP level, if you're doing HTTP services, wherever, you can copy the incoming calls and run them against your release candidate, and then just in an automated fashion, diff responses, just like you would do with that response diffing test. The difference here is that you're using customer traffic, right? And the key, of course, is you return the known good system's response to the customer, so they don't see anything if you screwed up. But this lets you use your customer traffic to produce the breadth of basically exercise your system the way your customers are going to, because you're not going to capture everything in the test cases you write. And it lets you test that load without affecting the responses you're sending back to your customers. There's one big problem with these, which is that you can't do this for things that change state, right? So read requests work fine, but if that request your customer sends in writes to the database, you probably shouldn't run 2 of it. Unless you've done a lot of plumbing to make it shadow the entire way through your stack. And then you're not actually testing the same thing. So instead, you can canary, right? This comes from the phrase canary in a coal mine. And all you do is just launch 1, maybe 2 hosts with your release candidate instead of a full fleet. Let them serve the appropriate percentage of traffic according to your load balancing scheme. And just watch it for errors. It's safer than doing a full deploy, right? Because it's faster to roll back, and you haven't taking down all of your customers, just some percentage of them if you screw up. Fortunately, you should have a bunch of testing in place, so finding errors at the canary stage should be rare, but it does give you an extra level of confidence when you're rolling out changes like this. And then now we've got our low-friction deploy system, and we have these extra techniques to give us extra confidence in our replacement systems. So we're ready to conquer that monolith. So let's go back to what I said about planning, which is that you should start with the easy and low-risk stuff, but then really get rolling, because otherwise you're going to be doing this forever. Deploy multiple refactors at once. we had dozens of endpoints to move with Starship. And when we got into the swing of it, we were rolling out 4 or 5 in a single deploy 2 or 3 times a week. So by the time we really got rolling on this, it only took us about 6 weeks to finally roll out and finish everything. The key here, as always, is to balance speed against risk, right? Move fast, don't break things. And finally, you can cheat. This is where I get to go behind the curtain or pull it back and show you everything what we actually did. You're going to get to a point in the refactoring process when you're replacing those old systems where you're down to the long tail, the stuff that gets 10 requests a day or is really not worth rewriting for whatever reason. Leave it where it is. And this is why I said to pick a shim that makes sense and is OK for you to live with. We actually still run some of the PHP API code. We moved it off, and we treat it as another internal service. There's nothing that says that Starship can't proxy to something that already speaks the public API, right? It's just a no-op. We moved it out. It doesn't run on the API host with Starship. It runs on its own fleet, so it doesn't consume resources, or it doesn't contend with the Starship API for resources. And really, you should think of this as keeping the old code around where it makes sense because it's not worth the time to rewrite it. But you're going to put a wall around it, right? So shove it off in a corner, lock it away, make it more attractive for people coming in who need to add new functionality. Make it more attractive for them to follow the new rules and play in the new game than going back to the old ways. That is all I have. This has been migrating from PHP to Python, really about how to get rid of those 500,000 lines of code. So to recap, those big bang rebuilds we all know are prone to failure. Incrementally replacing them is safer. And yeah, using these techniques, we did move 5 billion monthly requests to our API without causing downtime. Thank you. I hope I helped you learn something, and I think we've got some time to take some questions on this work if anybody has any. Okay, in the back.
Some really cool system you had where you were showing graphs of latency and number of requests. Could you talk a little bit about that?
Yeah, sure. So the question was, I was showing the graphs of our latency and our metrics. That graphing engine is actually a third-party company. It's called Datadog. And if you want to use them, you can sign up with their website. And all you do is they actually have a statsd interface. So you can just drop in their daemon on your servers, publish metrics to it from your code. You just make a library call and say, start a timer for this, or make a counter, incremented counter, and out it goes. And then they collect everything and put up the graphs for you. All right, also in the back.
Yeah, I was curious, because the name of the talk was sort of switching from PHP to Python.
Mm-hmm.
What? Most of what you talked about wasn't really specific to Python or another language or PHP or anything else. What was it other than switching from a monolith to a not monolith? And why did you choose the stack that you did choose to build on top?
Sure. So the question was, this actually wasn't very much of a Python talk. It's more of an architecture talk. It's valid. And why did we choose the architecture we did? And how do we validate that assumption, right?
Well, the stack specifically, because you also introduced a language change as well as the other changes that you did.
Sure.
And why did you choose that language as opposed to sticking with what you had or any other choice?
OK, so why did we introduce a language change as well as this architectural change? And why did we pick Python specifically? We liked Python for a bunch of reasons. First off, it's very easy to deploy, and you have a lot of options. As I mentioned, one of the performance issues we saw with PHP was that it's pretty hard to do async I/O in PHP. I think it's only really become a thing in the last year or so, whereas Python has had G-event support for a long time now. So we knew we wanted to get to async I/O at some point. So that was one aspect. We also liked that Python gives you, well, everybody knows it's batteries included. The library support is fantastic. Requests was actually a big piece of it. We knew this system was going to be doing a lot of HTTP, and we wanted to get something in place that was easy to write against, easy to test. So HTTP clients in Java are terrible. I don't know if you've used them. So yeah, I think it came down to the balance of how fast we wanted to get this thing written. Python is really great for moving quickly. We prototyped this. The original prototype came out in a matter of months. So let us move really quickly. And also, I just think It's a nice balance of performance, developer time, and flexibility. There are a couple things that we couldn't do in a statically typed language, for example. We do a lot of tricks just passing maps around instead of having to hard code all the data types. Given that we process so many things, we chose specifically to ditch trying to do static typing and say it's all just JSON maps. We'll write the validation code and do it at runtime. That make sense?
Yeah.
Great, thank you.
So I have a couple things. First, we did the exact same thing. I just finished the project here about 2 weeks ago. We used Node.js instead.
Okay.
And as you see, built one, so the model for the exact same
Mhm.
thing. But I had a question about your service infrastructure. So did you guys use containers? And whether or not you did, how did you manage service discovery?
Yeah, okay, so question was, what are we doing to deploy our services? We are not containerized yet. It's in the works. We run everything on EC2. And the other question was service discovery. So provisioning-wise, we run EC2. We have a custom AMI with some bootstrap in it that gets us up to the platform base, essentially. And then every team owns their own chef configuration to get their services installed on that base. And service discovery, we have a homegrown solution. It's basically the system of record for each Twilio environment is an API and a MySQL database that have the logic of managing services, groups, hosts, and load balancer state. The old world, we used HA proxy. Have you ever seen anybody use the upside down HA proxy or distributed HA proxy trick? So for anybody who's not familiar, this is instead of using a single load balancer running on one host, you put the load balancer code on all of your hosts and then configure it to listen on local hosts and then just route out to whatever's in the load balancer. And then you just need to glue that together to your system of record. So we have a pub subsystem effectively. There's a system that listens for changes in the state in the global service registry and then effectively updates the HA proxy configurations. Is that everything?
Yeah.
Okay. Oh, yeah, we've looked at that too.
You mentioned Java was used for all your integration to the communication system.
Yeah.
And Python was, well, and everything else was PHP.
Mhm.
And Python was used to redo your whole API. Is PHP still used for everything else? Are there any plans to switch that to Python?
Yep, the question was, do we still use PHP for things? Yes, we do. The website still runs in PHP. Probably 30% of the billing backend still runs in PHP. It's actively moving out into Python and also Scala. We basically have 3 stacks. We have PHP, we have Python, and we have the JVM. And whether people want to run Java, pure Java or Scala on the JVM is up to individual teams. I'm not sure where the split lies these days anymore, but we're pretty much going with the polyglot future. PHP, I don't think has any plans to go away entirely. The website runs fine with it. They've moved on to modern practices. So that's where we are today. Okay, anybody else? All right, thank you.